All the other types of polymorphism that we covered earlier. So we had ad hoc polymorphism, which is overloading. We had subtype polymorphism, which is basically the ability to substitute a type for another type. And in Java, subtyping is implementing using subclassing. So now the third type of polymorphism, parametric polymorphism. Just give me 1 second. Sorry. All right. Subtype polymorphism, and this is just a few review slides for what we already covered. Right. This is a list of rules that make up the list of substitution principle. Remember, covariance for the return types, contravariance for the parameters, and contravariance for parameters is not supported by Java, but in some other languages it is. Then this was a very important aspect of parametric subtype polymorphism in the presence of overridden methods. We might have several potential matches for a method with the same parameters, but different implementations in different classes. So when a class inherits an implementation, it may opt to override that inherited implementation with their other implementation. So given that, we had to talk about how the compiler and the runtime together decide on which method call to execute. That was called method invocation resolution, or method call resolution. All right, remember that the compiler makes its decision about the method family. A method family being defined as the name of the method and parameters. And then at runtime, only an implementation of a method from that method family is chosen. So at runtime, it may never happen that the runtime environment, JVM, decides to call a method from a different method family than what was decided at compile time. All right, so that was that. Yeah, so it's a combination of the compile time and runtime decisions. All right, and parametric polymorphism. All right, so that means that we parameterize not just functions or methods with some adjustable values that that's how we want our algorithm to adjust to different input values, but we actually want it to be adjustable also in the dimension of their data types, not just the values of parameters, but also the types of parameters. Right? So that is essentially what parametric polymorphism is. So in addition to taking parameters, their values for parameters, our code, or at least this is something that we would like to have. We would like our code to also take their type as a parameter. Okay. So, for example, if we want our code, we wrote a sorting method that sorts, arrays. Okay. And of course, we want our sorting method to work not on just a single instance of an array, but on all arrays with whatever the elements are, right? And that we can achieve with just regular parameters, right? So we make a reference to an array object, a parameter of our sort method, right? But what if then we want something more? What if we want our sorting method to work not just with arrays of a given type, like an array, like arrays of integers or array of floats, but what if we want to have our algorithm work with arrays of any type, be that integer, string, point to be objects, or something else? All right, so this basically takes this idea of parameterization one step further to saying, hey, let's have type added to our method definition as another parameter. Okay, and the way parametric polymorphism is implemented can be implicit or explicit. For example, in Java, their parametric polymorphism is implemented explicitly, as it is in C++, for example. Can someone give me an example of a language where we would have implicit parametric polymorphism? In other words, we would have the parametric polymorphism, similar to what I just described, and not having to use any special syntax for it. Just take it, just kind of get it for free, get it as is without really a lot of effort. Yes, please. Yeah, exactly, Python. So Python does support parametric polymorphism, but it does so implicitly, right? Because imagine you define a function that takes two arguments, a and b, and returns a plus b. Okay? So if I ask you, what are the types of a and b that this function expects? You can't really say for sure, right? Because that can be a number of things, right? With such a definition of a function, it can work where when a and b are integers, or floats, or lists, or tuples, or strings, right? Any objects on which this plus operation is defined, right? So it can work, this simple definition of a function can work with a variety of types. And you didn't even have to use any special syntax, right? Because in Python, you don't need to put down the types that you are expecting each variable to code. Right? So that was something that we were getting for granted. But of course, in Java, that would be not possible, right? To have implicit parametric polymorphism, because in Java we have to define types. Right, here's another Python example where we have this slightly more complicated function defined than from what I previously described, just a plus b. So we have sequence 1, sequence 2, and we go over everything in sequence 1, and then we check if it is in sequence 2, and we append the result list with the next. Okay, so how does this example differ from subtype polymorphism? So the answer to this is that subtype polymorphism is static, okay, and this is clearly dynamic. So if I ask you what are the allowed types for sequence 1 and sequence 2, in other words, what sequence 1 and sequence 2 could be to make this code run correctly. Yeah, please. Something iterable. Give me some examples.
String, list, set, I guess.
Yes, string, list, set. Yes, no. Is set ordered?
Oh, that's a 4. I was thinking about n as in like a check.
Yeah, so anything that you can go over in order, so a set you cannot directly, but you can easily convert a set to something that you can iterate over. And you see that this would be dynamic, so no one, you're never forced to tell in advance that, oh, I'm going to use this intersect with sequence 1 being strings. You can just call intersect with 2 strings and it would totally work. So you see that this is clearly not a static mechanism. This is a dynamic mechanism. All right, so if we recall what we learned about subtype polymorphism, then it guarantees that every subclass of the declared type will be, will work. In this case, will be iterable. Okay, so with a subtype polymorphism, the compiler, for example, would prevent calling intersect with two integers, like 2 and 3, right? Because they are not iterable. But that would be if we had types assigned, as if it were Java. But in Python, right, there are no types assigned. So of course, there is no compiler. So in Python, everything is dynamic, and there is no common supertype for types of sequence 1 and sequence 2. Right? So we cannot say that, this code would work with sequence 1 and sequence 2 being subtypes of some common supertype, because there is really no common supertype between a string and a list. Well, there is object, but other than that, right, there are no common ancestors. All right, so yeah, they can be completely unrelated types, more or less. Moreover, sequence 1 and sequence 2 do not have to be the same type. Sequence 1 can totally be a string. Sequence 2 can be a list. Right? That is perfectly fine. All right. Yeah, but that is Python with its explicit type, with its implicit parametric polymorphism, right? We don't have to declare the types, and it just works out of the box. All right, and besides Python, there's a number of other languages that follow the same kind of fashion. Perl, Scheme, other dynamic languages. Right, so yeah, you don't need to explicitly define types. The code just works with many different types by their virtue of dynamic typing. And of course, with Java, it's going to be different because we have statically checked typing, and therefore we would have to use explicit parametric polymorphism. And it's the same kind of requirement that yes, we have to go explicit with languages that do have static typing, like C++, Java, C#, and that means that we have to specify that we are going to use a type parameter. Right? So in other words, we would have to come up with some kind of identifier that would serve as a placeholder for our type parameter. All right. So this explicit parametric polymorphism is known as generics or genericity, and it is implemented in most modern programming languages. But it can be implemented slightly differently in different languages. So here's an example of C++ templates. So hopefully that rings some bells for you, right? So we have a template where we define that this is the class parameter in angle brackets, class V, right? So V is a class, and then we can use this V whenever we need to say, well, this is a list node where each element is an instance of V. All right, so that's how it looks in C++. And then once we define our list node, our data type, saying that, yeah, there is, as a template, saying that, right, we will allow our clients to use list node with whatever V they want, whatever class they want. Right? Then when the client actually uses our list node, they specify what type they want to essentially substitute for V, or which type they want to use as that generic type parameter V that we were using when we defined our list node data structure. All right, so yeah, that's their use side of their templates, and in C++, it generates an entirely new data type. So what physically happens with C++ code, when someone uses their list node like that, specifying int as a type argument, then a new type is created. So basically, this template is expanded, v is replaced with int, and this becomes the definition of a new type. And typically we would use it with a type def, so the name of this new type would be int list node, right? Then we can use this int list node just as a type to define our variables, or we could type def list with an int and call it int list like that. The problem with this approach is that there is a new data type generated for every single value of, or every single use of a different type argument. Right? So if our user needs a list node of ints, a list node of shorts, and a list node of arrays of characters, they would be three different types, and C++ compiler will generate three different definitions for those types. So it bloats up the code significantly, right? Because it will generate a new definition of the type for every different value of their type parameter. Right? So multiple copies of the generic code. This is one of the consequences of such an approach to implementing genericity in C++. That sometimes, in fact, quite often leads to extremely unhelpful error messages where you make just one little single mistake in your source code, and you're getting like several screens of output of errors complaining about something related to templates, which it's really very hard to decipher all those messages, right? Because they don't point directly to the line of code where you made this mistake, because they can only be detected after this template expansion happens, and at the time there's no way to trace it back to the original line which caused this this whole problem. All right, so partly because of that, Java uses a different approach to generics, which of course is it has some advantages, but it's also not free from problems, as we shall see shortly. All right, so yeah, I mentioned about the massive amounts of unhelpful error output for C++. All right, so in Java, the parametric polymorphism is implemented using a mechanism that is known as generics. On the surface, it looks somewhat similar to how we define new types with parametric polymorphism in C++. So we still, when we are defining a new type that needs to support parametric polymorphism, we have to we have to come up with an identifier that would be this placeholder for the actual type. And then when our clients use our type, they need to provide their type argument, right? So the type argument is gonna get matched to their type parameter. Right? So it's conceptually similar to how when we define a method, we specify parameters. When we call a method, we provide arguments, and arguments are matched to parameters positionally. First matches to the first, second matches to the second, and so forth. So it's conceptually similar with generics. We have to, when we define our class that we want to be generic, we specify the type parameter. When we instantiate our class, we have to specify the type argument. So in this example, ArrayList is a class that has already been defined, right? So we are looking at the use side of it, not at the declaration side of it. All right, so we're just looking from the standpoint of their client that wants to use ArrayList. ArrayList is generic, which means it expects us to provide their type parameter. All right, so this A type has to be a concrete type, like int or string or something like that. Well, with int it can be a little tricky, but we'll get back to it. But yeah, like string, point to the person, that any of that can be placed here instead of a type. And not just the concrete classes can have type parameters, but even interfaces can be made generic. So here on the left, we see that this list variable is declared as having type list. List is an interface with their type argument, whatever, a type, string, point to d, whatever. Okay, so interfaces can also be generic. All right, and then the easiest case is when we have this A type that is the same for when we use it as type argument for list, the declared type of the variable, and ArrayList, the actual object that we are creating. So this A type is the type argument, and yeah, this is the most straightforward way of using generic types. So we define names as a list of strings, a list with a type parameter string, and then we create an instance of ArrayList with a type argument string, and we assign this object to variable names. Of course, generics, parametric polymorphism, does not clash with subtype polymorphism. So you see that the mere fact that we make names have their static type, have their declared type, different from the type of the object which we are assigning to names, means that we're using subtype polymorphism here, right? Because list is an interface, ArrayList implements this interface, so from the standpoint of their type system, ArrayList is a subtype of list, and that works, right? So this is subtype polymorphism right here, in addition to parametric polymorphism, which manifests itself here with their angle brackets, that those less than and greater than characters that we have here, because both their interface list and the class ArrayList are generic. And any type that is generic, it is highly recommended that you actually use it as such, that you supply the type argument. Because technically, yeah, you don't have to do this. If you, skip string in angle brackets here and string in angle brackets here, your code would still compile and most likely work, but it's going to be a lot less safe in terms of ensuring the validity of types, and therefore it's possible, but it's not recommended. And we are going to return to this discussion of why it is allowed to begin with, and why it is strongly, people should be strongly discouraged from using generic types as non-generic types. All right, so once we have defined their variable names and assign an object to it, then we can start using any methods and any accessible methods, any accessible members, any accessible fields of this class, of this list interface in this instance. And then all methods that are in the implementation of ArrayList, right? All methods that use the type parameter would automatically be adjusted to use the type that we specified when we instantiated our generic. So this add method in ArrayList is defined as taking their, let's call it E, right? type parameter, right? When we specify that instead of E, we're going to be supplying string, then there's this connection between, anywhere in the definition of array list you see E as a type, replace it with string, right? And therefore, method add would now be expecting string and nothing else but string. So if you attempt to call add and give it a point to D object, the code would not compile. And this is one of the biggest advantages of using generics, because it strongly enhances type safety. You wouldn't be able to violate the guarantee of the compiler that if the type argument of this instantiation of array list is string, then no code would compile if it violates this type safety. No code would compile if it has names.add 5, for example. Okay? Of course, it works equally well for the return types as well. So get method gets the first element from the list, and the return type of get is also linked to the type parameter, the same type parameter that we instantiated here as a string. So now our get method returns a string. So this first line works perfectly fine. What about this second line? Well, the second line will not compile, because what we get out of their names can only be a string, right? Because we instantiated names by specifying the type argument as string. So this code would simply not compile, protecting us from inadvertently treating a string as a point, right? Which of course wouldn't be, in general case, wouldn't be safe. If for some reason we believe that it should be safe, then we have to pass on this guarantee to the compiler. Then we have to say, well, whatever I get out of this names list, I believe and I guarantee, as as the person who writes this code, I guarantee that it's a point, and therefore I'm attempting to perform this cast here so that this assignment can actually work. But unfortunately, even with this guarantee, the compiler is smart enough to figure out that no, that's not possible at all, right? Because string can never be a point. String and point are two classes that are not related by inheritance whatsoever. So there is no way this assignment can be safe, and that's why this last line will also be a compile time error. But if there is a possibility that this cast can be valid, then the compiler would just take my guarantee and compile this code. For example, if we had names as a list of integers, right? Big I integer, not the primitive value, but their boxed value, big I integer, and if this p was a number, right? Then this assignment would work even without the need for a cast, right? Because a number can be assigned a reference to an integer object. What about if we flip that? What if the variable is declared as integer and names is a list of numbers? Well, then it may work if we actually have an integer in this list of numbers, and then we would have to provide the compiler with a cast. We would cast it to the integer, right? But again, this would be our responsibility. What if that object turns out to be not an integer, but let's say a double? Then we would get a class cast exception. So the compiler would still let this code compile, because it might be a valid cast, but if it turns out that it's not valid at runtime, it would give us the class cast exception. So anytime you find yourself writing those casts, be extremely careful. A rule of thumb, you shouldn't be writing any casts, with very rare exceptions. When you are when you undertook all the precautions to make sure that this cast is actually going to be safe. Okay? If you're not sure, do not cast, right? Because then there is a possibility that your clients will get class cast exception. For them, it means it's a programmer error, right? It's not a checked exception. It's not something that anyone expects to see from properly working code, so it shouldn't be done, right? And to link this to what we previously discussed about identity and equality, right? Remember back there we were using casts, but we were super careful. We would first check if this object is actually an instance of this type, and only if the instance of was given as true, only then would we apply the cast, right? So that was safe, right? But without that, doing just like that is not this last line is not safe, right? So even if the types are potentially compatible, which in this example they're not, so as I mentioned, this code would just not compile to no matter what. All right, so we just looked at the use side of, or instantiation side of generics. So and you have had some experience using generic types, mostly collections. So let's now look at their declaration side.
Two things. First, there's something weird going with the audio where like after you speak and like there's some kind of like, I don't know, could you mind sort of turning it down just like a tad bit?
Well, let me see. Is that still good? Still echo?
Yeah, it sounds like like a like you said, sounds like a balance. Yeah. It should be fine
How
now.
about now?
Now it's good.
Okay.
And then
Thank you. All right. So what we are, it's very easy to use a generic type, right? So like here, this is something that you've done before, right? If you needed an array list to store, or in a hash set, or a hash map to store your labels for your graph, you would just use one of those collections. Hopefully, you would specify the type, which was string, and that's it. Okay, so very easy. But how about defining the types to be generic? And here things get a little harder, but still not too bad. First, I think that we need to mention is that in Java you can make a class generic, or you can make a method generic. So there are generic methods, there are generic classes, and they are basically orthogonal. So it doesn't mean that all methods in a generic class are generic. No, you can totally have non-generic methods in a generic class, and conversely, you can have a generic method in a non-generic class. Okay, so there are just two different things you can you can come up with. So let's first start with generic classes, right? Because it's arguably a somewhat more common case than having generic methods in a non-generic class. So by definition, a class is generic if after the name of the class, when you are defining the class, you put angle brackets and you list your type parameters. Again, pay attention to the terminology. This is called type parameter because it's just a placeholder, like a variable name. This is called type argument because this is their actual name of the type that you want to use this array list or my set with. Right? So type argument, type parameter. Right? So when you are defining, first you have to specify the type parameter. And in this case, it's just t. So t is just an identifier. It doesn't have to be capital case. It doesn't have to be a single letter. All right. So it can be any identifier. Java generally allows for classes, variables, class names, variable names, method names. But the convention is that it's a single letter and that it's a capital letter. But again, this is just a convention. We ask you to follow it, right? But if you want to, try violating those rules, the compiler is not going to stop you. We might, we might give you a slight reduction for not following Java conventions as far as manual grading, but the compiler is not going to stop you. All right. So what are again, this is just a convention. What are the typical names for type parameters? Well, T is probably by far the most common because it's in a natural sense for type. Right. Another popular choice is a pair K and V because they can stand for the type of the key, the type of the value. Right. For any data structures that naturally operate with pairs of values. In general, you start with, if you need multiple type parameters, you can list more than one. So you can put a comma after T and then specify your next type parameter, your next. You can have many type parameters. All right, so typically, if you have type parameters that and you name your first one T, then the second one would be U, and then you would use V, right? And just use parameters just selecting their consecutive letters from the Latin alphabet. It's not very common to call type parameters A, B, and C, right? So try not to use identifiers from their from the first part of the alphabet, but there might be exceptions. For example, if you need to specify something, the type for the labels of your edges and the names of your nodes, you can totally use E for the type of edges and N for the type of node. Right? That would be okay. All right. So this is what makes the class generic. Okay. This basically tells the compiler that, hey, I'm defining this class which is going to have type parameter, and this type parameter is T. And then once this type parameter is declared, you can use it anywhere in the definition of your class as any type, right? As the type of their of a field. For example, this last up field has type T. That you can use it to instantiate other generic types. For example, we use T to instantiate list. So we're saying, well, there's going to be the list of T's. All right, and remember, T is not a real type; it's just a placeholder, right? But whenever someone uses our mySet with a specific type, so this is called instantiation. So here, our client instantiates mySet with a type argument of string. So what happens? This string is going to, basically replace all T's in the definition. Right? So the type of last looked up is going to be string. The type that is used to parameterize list would be also a string. All right, so you see how this system is extremely flexible. Whatever the type we instantiate with is going to be bound to the type parameter that we declared when we define our class. All right, so what happens if we forgot to if you forgot and you didn't write this, right? What if you forgot to write this? This code is not going to compile because it would be like, well, the compiler doesn't know what this T is, right? Because you are referencing a type parameter which is not declared anywhere, right? So that's not going to work. But what if you define your class so that it doesn't have this and it doesn't have this? Will that still be okay? Yes. Because yes, it's a generic class, it has this type parameter T, but you ended up never using it, so it's probably not making a whole lot of sense but this code would compile. There's no error in defining a type parameter and ending up not using it.
That should make money.
Okay? And of course, yeah, you don't want to do this on purpose, right? Because if someone is reading your code and they see this T, they can expect that this T is going to be used, that it's there for a reason, right? But technically, this is, that's from the standpoint of language, it's not a violation. It's like, remember, you define a method that takes 3 parameters, A, B, and C, and then in the body of the method, you only use A and B, you never use C, right? Yeah, it's a little strange, but all right, the compiler wouldn't mind. All right, so note that, of course, we can instantiate this my set, the type that you define, with any other valid reference type. So here we can say my set of strings, here's my set of integers. Right, so you can use anything for T. Right, in this case, there are no restrictions, but it has to be a reference type, which means we cannot do primitive values. So this is not a valid syntax. There is no auto-boxing for types. Right, there is auto-boxing for values. So if you have code that expects a primitive that expects a reference type an object and you give it 5, then yes, it will auto-box this value. But that doesn't work for type inference, right? So it's not going to promote int to an integer by itself. So you have to use big I integer as the name of the type, not one of the primitive types. All right, and finally, one last note related to what you see here is that in Java, there is no template expansion that happens, which means that the definition of your class only exists here. There's only one copy, right? And whenever you use a different type parameter, right, that does not create multiple copies of my set, no matter how many different instantiations you have. So in that sense, it's a little better, a little more economical than it is with templates in C++, but there is a big disadvantage to this mechanism as well, which is called raw types, and we can talk about that shortly. All right, so now moving on, this is the general syntax, so we can have multiple type parameters for when we define a class. Remember, the type parameters have to go right after the name of the class. This is the name of the class, and type parameters have to be right after that name. Not before the class keyword, but exactly here. And as we mentioned, the most typical generic name for the type parameter is T, and then U, V are common, but you can also use E and V depending on the semantics, and E for just a general element of something, and N for number. But the other convention is that it's a one-letter identifier, and that letter is capital. All right, so instantiation, we have already seen how it happens, right? We have to specify the concrete type, and this type doesn't have to be a concrete class, right? So it can totally be an interface if you want, right? So, but it has to be a valid specific type. All right, so that's that, and now let's look at an example of a generic interface. All right, so imagine this is actually how the list interface is defined in the standard library. So note that it uses type parameter E, which stands for element, so that this code is easier to analyze when you imagine E being like it stands for element. And then methods use this type parameter. All right, so here add takes its argument that should have the same type as whatever the type argument was supplied when this when the client instantiates list.
Is there a way to kind of like prevent the client from passing in a bad type, like the example before with int, or is that kind of like something that you just gotta say like put in the requires clause and hope for the best?
An int, the client would never be able to pass because it's not a valid reference type. So that is something you're protected from. But so far, you do not have any methods of restricting what type they can use with, when instantiating. So it can be string, integer, point to be, object. So far, it can be anything. But yes, you can actually limit what they can what types they can instantiate your generic class with.
So there's no way to take that and auto-box yourself?
No, it's not an autobox because it's a type. Autoboxing only works on values. Autoboxing is creating an object that contains, this primitive file, right? There is no objects here, right? There are just class definitions. Int is a type, or type definitions. Int is a type. Integer is a type. There are no objects involved here. All right. One other thing here. The angle brackets you only use when you introduce the type parameter. Okay, so you don't use angle brackets when you use this type parameter. Here, all those examples are using type parameters. So here you say that get will return whatever that type e is. Okay, here you're saying set will take an integer and an object of whatever type e is. Okay, that's how you parameterize your type, your list interface in this case, right? So that when someone subsequently declares a variable of type list with something specific, right? That something specific will be bound to this e. All right. And of course, when you implement a generic interface, right, it makes sense to also make your implementing class generic. So public class ArrayList E means that this is the type parameter for your array list. And it implements a list, and list is generic, and you use the same variable here. You don't have to, but typically this is what we want. So that you basically say this is the same E as this E. Okay? Because if you use here, right, you are instantiating E. And if this type is unknown, your code would not compile, right? If you put B here, right, your code would not compile because it has to be, it's using list. So it has to be some known type or their type parameter that is defined in their class that implements this interface. So V would not work here. If you put some specific class, yes, that would syntactically work, right? Because then you would say, well, for any array list, it implements list with a string. It doesn't make a whole lot of sense, right? But yeah, you could do that. You can essentially list with a specific type. But of course, it rarely makes sense. So when you are working with your graph, all right, make sure that if you have a certain interface, you have their implementing class using the same type parameter here and here. All right. So why generics are so loved? Yeah.
I just want to double check. So you can't do that. Actually, I'm gonna curious. Can you do where you can you go back a slide?
Yeah.
So when you say public interface list E, can you also say list and then E comma E if you want them to pass the same thing again in a size, like if you want to have two kind of generics of the same type, if that makes sense?
you said again, to generics?
So like, can you say instead public interface list and then E and then comma and then E again? Or is that something, okay, or do you have to have
Like
like,
that? No, because here you're just saying, well, I gotta have type parameter E, right? You cannot, so if you want two of them, you want them to be different, right? If you want them to be exactly the same, just use E and that's it,
just, okay.
right? So basically, like, what you're saying is when someone uses your list and you want to force them to write string, comma string, and make sure that they, these two types are the same, right? But then you don't need E comma E for that. Just use E, right? And that would guarantee, and then you would force your client to repeat this string. Just use E and say, well, this list needs one parameter, okay? And then you can use it multiple times, but it's one parameter. If you need two, then you don't want them to be always the same, right? So for example, if you want your list to take E and F, right? Then you actually want to allow them to be different, but you do not require them to be different. So someone could use your list with string and string, or string and integer, or string and something else, or integer and string, right? So you want to allow them to be different. If you don't, then you don't really need two type parameters. All right, so why generics are so good? Believe it or not, they help to clarify your code. I don't know if you would agree based on the examples that we have seen so far, because they might look a little confusing, but generics actually help you make your code more universal, so that your sorting method can work not with just strings or integers and forcing you to implement your sorting method for all the different types that it supports, but capture the idea of the sorting algorithm irrespective of the specific types. Because really, the sorting algorithm doesn't care what it is sorting, as long as whatever it is sorting, you can compare, right? You can sort people, you can sort chairs, you can sort universities. Doesn't matter if you can compare two objects and determine which one is smaller or greater. That's all that the sorting algorithm needs. And the concepts like that are very easy to capture with generics. And historically, in Java, there were no generics. So generics only appeared in Java starting with version 5, which was like good 15 years, if not more, after the language was first introduced. So for the first 15 years, there were no generics in Java. And you might be wondering, well, how did all the collections work? Well, they work by just being defined using the most common denominator across all the types in Java, and that would be object. So all collections were implemented using object. Okay? And yes, that worked because in a collection that stores objects, you can put anything. Right? That was fine. So here's what their old Java code would typically look like. Right? So you would have a map, right? A new hash map, and you could put a key value pair, which would be a string and a hash set. But then nothing would prevent you from putting into the same map a pair, which would be an integer and a point to d, right? Because there was no control. Anything that is object compatible would go into this collection, right? So that was a lot harder to enforce, that a collection only stores certain types of elements, and that was of course causing problems when you were extracting, when you were getting things back from the collection. So for example, called get. You give a key, and you are never sure what the actual type of the element that you get from the collection is. Right? From the only thing that you know, it's an object, but you don't know anything more specific about that element. So if you if you are sure that I put a hash set there, then when you get it back, it's still a hash set, so you can use a cast, right? But what if you got confused and you extracted something? You thought your key was that, but your key was different, and what you extracted was not that key value pair, but a different key value pair where value is not a hash set. Right? Their collection itself would not care what their value is, whether it's a hash set or a linked list or a string or an integer. Right? They all look alike to the collection. They all look like objects, so it doesn't care, and it has no way of checking. So you would be forced to do those casts, and then if you are wrong about the type of the element that you just received from this collection, you would get a class test exception. Okay? So that was sort of inevitable. That was making code a lot less safe. And that was their primary driving reason why generics were introduced in Java eventually, and all collections, as of version 5 of Java, all collections were rewritten so that they now use generics. Okay? But because of the fact that generics were an afterthought, they were not part of the original design of the language, that created a compatibility issue, of course, because previously that's how you would use your collections, right? There was no syntax of angle arrows, right? It was just not valid syntax in earlier versions of Java. So now that you have this angle bracket syntax, right? That you would have to use. All right. So how would all old code work with the collections that are now generic? Right. The old code that does not have those angle brackets, and inevitably they had to settle on a compromise. They would say, well, old code will still work with the type parameter being object. Okay. So old collections or the old style of using collections with the newer versions of Java, post 5.0 or 1.5, it's the same thing, would be, it would just use object, okay, as a type argument. And that means that instantiation of a generic is only a compile time concept. In other words, when your code is compiled, when your beautiful generic code is compiled, it is actually converted by the compiler to something as ugly as the original Java code with objects all over the place, right? The way the code looked before generics were introduced. All right, so yeah, it's a little ugly, but Java is not the only language that suffered from it. C#, which is a much newer language, in version 1.0 still had no generics. So, but in C# they added generics in version 2.0, but it was still good 3, 4, if not 5 years after the first version of the language was introduced. Okay, so because back in their mid late 90s, they were just getting to the idea of the fact that generics are a useful feature of any programming language. Okay, so many languages back then did not have generics, and then we're coming up with generics as an addition. And C++ is no exception, right? So there are no templates, of course, in C. So templates were also added in C++ compared to the original plain old C. All right, so Of course, our code with generics is a lot safer, right? Because now we specify type parameters and we use them throughout our code. So KB and KB and V here, right? So those are usages of this is their declaration of type parameters. We have two of them in this example. And then when we instantiate our map, we have to provide two type parameters, right? Any type argument can in turn be any valid type, right? So yeah, we could have instantiated map with, for example, integer and string. Right, that would be totally valid. Then k would be an integer. Right, so k here and here would be an integer, and v would be a string here and here and here. Okay, so that would be one valid instantiation. But if we want one of the types to be more, not string, but a hash set, we can, right? But hash set is a generic type, so it has to be in turn instantiated, right? So there's nothing wrong, but the syntax is looking a little, a little harder to digest because you have, this sort of chevron, right? Two closing angle brackets. But it's only because we decided that the value for our hash map is going to be a hash set. Okay? So the key is a string, the value is a hash set. Hash set in turn is a collection. So we want elements of this collection to be strings. What if we wanted values to be a hash set of hash sets of strings? That would still be possible, right? It's just instead of this string here, you would put a hash set of string, right? And you would have, in total, 3 closing angle brackets.
So like V and K, they're like really like umbrella terms, or like they can hold like other, I guess, generic objects. I don't know what the proper terminology is, but like they can hold like something else that like uses generics, and that's okay, right?
Yeah, so V is basically a placeholder. When you define your type, you say, well, V is a placeholder for some type. And when you instantiate, when you actually use this type, like this map interface, you say, well, this is going to be mapped to the first type parameter, K, right? So this is called the type argument. The first type argument is mapped to the first type parameter, K, and this second one is mapped to V. So whatever this second thing is, the entire thing is V. All right, so the benefit, right, the huge benefit, the most significant benefit of generics is the fact that you make your methods and fields parameterized with the type parameter. So you make them strongly typed, right? This put, instead of just taking an object or an object, it takes exactly K and V. So it takes exactly a string and a hash set of strings. So if you attempt, instead of giving this put key, which is a string, if you attempt to give it a 5, the code would not compile. And you actually want it. You want your code to fail compilation because compilation errors are easy to fix. Runtime errors are a lot harder to fix. Right? In the case of, imagine before generics, your collection would take this 5 and value, okay? But despite the fact that it's not the type that you wanted, but there was no type safety here when you were dealing with collections, and that was very very annoying. So now with generics, it's a lot safer. This code will simply not compile if the type of key is not string, or if the type of value is not a hash set of strings. Right? And similarly, when you get something from the collection, you know that the return type of get is exactly V. So in this example, it would be a hash set of strings. So if the type of the variable neighbors is not a hash set of strings, then this code would not compile. Okay? So that is, that is great from the standpoint of type safety. All right. So a side note, I briefly touched upon this. So why does Java not allow primitive values like ints to be used as type argument? Well, the reason is because generics were a late addition to the language. Internally, when the code compiles, it is their old type information is erased. This is called type erasure. So basically, when you spend all the time defining your key and then using your key, this is just for the compile time. This is just for the compiler to check your types, and if the compiler is not happy, it fails compilation. And you're glad because you are able to see the problem with the code right away. But if the compiler is satisfied with all your types, so it did all the type checks and it found no errors, then it compiles the code and it erases all type parameter information and reduces your key to an object. Right? So it's not an object internally. Okay? And that's how they, at the same time, solve the problem with compatibility. Right? So their code that is unaware about generics would just keep using object, and it is called raw type. Using generics as a raw type is considered to be essentially a mistake, right? So if you have no reasons to write your code so that it compiles with pre-Java 5. Okay, so all the types that have that are generics, make sure you use them as generics, right? Because there's absolutely no reason not to, right? Please, and I know sometimes it may take a certain amount of effort to fix your generic code when you work on the homework. Just deciding, oh, I'm just gonna just zap all those angle brackets and then just gonna go with no generics at all is never a good solution. Okay, so we will be keeping an eye on this in when we do manual grading for the next homework, right? Because that requires you to use generics. Okay, because and the reason is because we are raw types are inherently unsafe in terms of types, right? You basically turn off all the type safety checks, and there's really no reason to do that. It's a much better idea to finally get comfortable with generics. All right. So if you work on your code on the local machine and it complains about something like you using a raw type, and it's a warning, because yes, technically code would compile, but please make sure you do not have any of those warnings left in your code, because we will be watching for those warnings as part of our manual grading, and we will penalize for those warnings on homework 6, right? Because you should not have any warnings related to generics. All right. This is just an example of how your code would become unsafe if you use raw types. All right. So yes, if it happens internally after compilation, after the compiler checked all their type, ran all the type safety checks, this is safe because it checked that however you use whatever get data returns is use it as an integer, right? And it ensures that you could only place an integer or a subtype of an integer when you call the add method of that container. Okay, so the compiler, after running those type checks, it guarantees that you will not see a class cast exception here. Okay? But if you use raw types, then it's on you to perform those type safety checks. And if you do not perform them well enough, you might see, or rather your client might see, a class cast exception. So this is essentially what type erasure is. Generics in Java is purely a compile type safety mechanism, and that kind of explains why we do not see this, instantiation of templates, as is the case with C++, right? Because really, after compilation, there are no different types for different instantiations of the generic type. There's only one type, and internally it uses an object. All right. Now back to the question of, well, what if I want to limit the user in what type they can instantiate my class or interface with? So first, why would you want this? Why would you want to limit the types, right? Wouldn't that be better to give your user more freedom? Like here, right? We do not specify what K and V is. Why do we have to? And the answer is, if you think about the future implementation of this put method, right? If you have this key variable, think about what you can do with this variable. What do you know about this variable? What methods can you call from this variable? And the answer is, well, you don't know anything aside from the fact that it's some kind of object, right? You know it's going to have some type, but you don't know what the type is. So you would only be able to access fields and methods that all objects have, right? And that would be only the types and fields that class big O object defines, right? So you don't know anything else about this key in the definition of your interface, of your map interface. And that can be very limiting. For example, in this case it's not limiting, right? You don't care what that key is. But what if you wanted to call method M on this key, right? Then you have to make sure that key is an object, an instance of a class that is guaranteed to have this method M. Okay, and that means that yes, now we have to limit our client so that they can only supply the type argument for K, the type argument that is a class that has this method M. Okay, and that is a very common scenario. That's why we need quite often bounded type arguments, and to specify in the declaration of the type parameter that you want it to be bounded, you use the extends and then the type. So that tells the client that when they instantiate your mylist2, they can supply a type argument, which is a number or any subtype of a number. Right? So in other words, this E has to be a number or a subtype of a number. That's why when your client instantiates mylist2 number, it's fine. Mylist2 integer, it's fine because integer is a subtype of number. But when they attempt to do mylist2 date, that's not a date because date is not a number and not a subtype of a number. All right. So what this allows you to do is now when you have somewhere in let's mention and of course it's interface, so we're not going to have any implementations there, but now imagine that you are defining a class that implements mylist2 and it has some variable key, okay? And now it has type E, but you know that E is at least a number. So you know that you can use key to call any accessible method of a number, class number, or access any accessible field of class number, right? That is why you typically want to limit, to bound the type arguments that your generic class should be instantiated with. All right, so yeah, we basically discussed this, right? So perform operations permitted by the bound, because without the bound, you only know that your class is an object, right? So here, without the bound, it defaults to extends object, and then you cannot call int value from an arg, right? Because depending on how your mylist1 is instantiated, e might be the type that does not have int value. So if you have e extends number, then you know that whatever your mylist2 is instantiated with, whatever the type argument is, it is number or a subset of a number. And all of them, both the number and all their subtypes of the number, would have int value. So this is okay. All right, more details about upper bounded type parameters. So the general syntax is type extends some specific type. So this type is a type parameter, and this some type is a specific type. All right, so there are three effects that specify their upper bound. A type parameter has first, it restricts instantiation, which means that whoever uses your type would only be able to specify a type argument, which is a number or a subset or a subtype of a number, like an integer. From the standpoint of access to non-static members, all right, so you are now, if you have an upper bound specified, that allows you to access all non-static accessible fields and methods of the upper bound of number class in our example. And then type erasure, right? So when type erasure happens for bounded types, then it goes not all the way to their object, as was the case with unbounded types. Right, so with unbounded types, it goes, as a result of type erasure, it goes all the way down to object. With bounded types, it would go to their bound, right, to their type that you specified as your bound. So in this example, with type erasure, this example, E in your code will be replaced with number. Not with an object, but with a number, right? Because whatever that E is, it is guaranteed to be at least a number, maybe a subtype of a number, but none of their classes that is not related to, not a subtype of a number. All right, so that's that. Low bound type parameters. Is that a thing? No, Java does not allow bounding in the opposite direction. So no, you cannot do T super number. No, that's not something that Java allows. All right, so but if it so if it were allowed, then it would just work in the opposite direction, right? So it would require that type parameter is a super type, and that type erasure would essentially be replaced by object, so the result would have the same effect as no bound at all. All right, so this explains why T super, so lower bounded type parameters do not really make a whole lot of sense, and that's why they're not implemented in Java, right? So they don't really give you much, but they can be confusing. All right, so, we don't have that much time left, so let's skip this exercise for now, right? But we can see that given this hierarchy, X, Y, and Z, you need to select valid instantiations of generics. So let me, right, so, all right, so here, A with the type parameter Y, all right, so let's just do one, all right, so Y extends X, so T extends X, yeah, it works. A with an X, yes, it works, because T is an X. A with a Z, yes, it works, right, because Z is a subtype of X, Z extends X. And if we we have a t extends z, then a with the type argument z works because z extends z, but not a with type argument y, and not a with type argument x. These do not work because neither y nor x extend z. All right, so those were generic classes. Now generic methods. Right, so you can make a method generic by letting it define its own type parameter. So note the syntax is somewhat confusing because note that there are no angle brackets here. So it's not a generic class, right? It could have been a generic class, but it doesn't have to. So we can totally have generic methods inside non-generic classes. Okay, and if our class were generic, we would have angle brackets after the name of their class. To define the type parameter for a method, we have to put their type parameter before the return type of the method. So not after the name of the method, which would be here. No, not here, because for the class we don't have anything else. Right? When we define a class, after the name of the class, we don't have anything else. We only have this opening, this curly brace that starts the definition of the class. In case of their method, we have the regular parameters in parentheses. So we cannot put anything here. That would be too confusing, even more confusing. That's why they decided that their declaration of type parameter should happen earlier, not here, but before the return type of the method. Okay, so that tells us that this SUMList method is going to be a generic method. Right, this makes the method generic. Right, angle brackets introduce the type parameter, and then SUMList now gets their ability to use this type parameter t anywhere to represent a type. So in particular, SUMList says that its return type is going to be t. Right? So this t stands for here the return type. Right? Again, SUMList doesn't have to use a t for the return type. SUMList could have returned integer or string or any other type, but it may decide to use the type parameter as their return type. It may also have the type parameter used in the parameters. For example, SUMList expects a collection of elements of type t. So those are, right, this here and this here is the use of type parameter. Here, it's their declaration, introduction of the type parameter. All right, so generic methods, right? There are a few things that we need to know about generic methods. Generic methods, they are generic because they can be used with arguments of different types. Remember that when you declare a type parameter, you have to use the angle brackets before the method's return type. Okay? So each type parameter section contains one or more type parameters. So we only have one in this case, but it can be more than one, right? If we wanted to, we could have added a comma here before the closing angle bracket and say u and v, and each of u and v could be bounded, of course, right? So a generic method can have multiple type parameters. So that type parameters can be used throughout their method. For example, it can use it as their return type, or it can use it as any other method for any other variables, including the variables introduced in their list of parameters. Of course, when we instantiate, when we call this generic method, we have to supply their concrete type that will be mapped to their generic type parameter, and those types cannot be primitive types, right? They have to be classes. They have to be reference types. All right. So here is a short example where we are trying to come up with a universal method that can print elements of any array regardless of the type. So that's why we make this print array method generic. So this is declaration of the type parameter. But note the class that print array is in, this class is not generic, and there's nothing in here. So it's not a generic class which has a generic method. It's totally fine. So once we introduced E here, we can use it here to specify that our print array expects an array of elements E, and then in our for each we can use E to specify the type of the element local variable, and here we are. Right. So once this print array is defined, we can use it for to print int array, an array of integers, an array of doubles, right? Any array of any type. Okay, one thing is, well, what if we want to kind of expand on our success with the print array method and say, well, I want to write a universal sort method that can sort anything. So it takes a list of type T, and then at some point inevitably it will need to compare elements E1 and E2. Okay, of course, in order for this to work, you have to bound T, saying that T is any type, but it has to be comparable or a subtype of comparable, right? Because comparable provides for this compare to method, right? Any other type that is not comparable is not guaranteed to have this compare to method. All right, so that's that, and with this, here is our similar to sorting, but slightly shorter because it's a maximum method, right? So, but it is a generic method, right? No, again, this is not a generic class, but it's a generic method with a bounded type parameter saying that T extends comparable T, and it takes 3 values, all of type T, it compares them and returns the max. Note that this is the return type of maximum. It is T. So when we call it with integers, the return type is an integer. When we call it with doubles in this case, it returns a double. Okay? When we call it with strings, it returns a string. Right? So that's very neat, right? We are capturing the algorithm regardless of the type that this collection has. All right, so finally, what if we attempt to do something like that? Write a universal copy method that would copy elements from one list to another, and just make it generic so that those elements can be anything. All right, we just follow the example that we have seen earlier, and write our code like that. And unfortunately, that is not going to work as expected. Well, it is going to work as expected, right? But we shall see shortly that further development of this idea would just fail. And the reason why is let's look at the type compatibility between different lists that have the same type argument here, T, okay? But when instantiated, nothing prevents us from using list number here and list string here. We don't get a compile time error, right? So good, right? Because this T has to be the same as this T. All right, another example. What about string and object? Again, compile time error. What about object and string? No, cannot do this either. So it can only work if the types are exactly the same, string and string. Okay, so that kind of works, but we see that it's a little too limited. Right? So for example, we cannot take an element from a list if it is defined as an object, list with type argument object, and have our copy method copy those lists, right? So in the current form, our copy method is not hugely useful because it is too restricted, right? It requires that it is exactly the same type for the source and destination. So how can we try to get around this problem? Well, what if we say that the type of the first list, the destination list, is a super type of T, and their type of their list for the source is a subtype. And unfortunately, this is a worthwhile idea, but unfortunately, this code is not going to compile in the present form. And the reason for that is that T2 super T means that T2 is a super type of T. And T3 extends T means that T3 is a subtype of T. Okay? So that makes T3 a subtype of T2, and that makes sense, right? So the destination list should be able to store all elements from the source list. But unfortunately, this is not trivial, because it turns out that type parameters, they do not carry their inheritance relationship over to the types where they are used as type arguments. In other words, T3 is a subtype of T2, but that doesn't make list of T3s a subtype of list of T2s. Right? And this is probably the hardest concept to understand about generics. Right? This problem, we would still be able to solve it, but we would introduce the wildcard, this question mark. Right? So more on this later, but for now, let's see why such a problem exists. So we know that an integer is a subtype of number, no doubts about that. But is a list of integers a subtype of list of numbers? And the answer is no. Okay? Because it's not guaranteed in general, right, that any list of integers would be also compatible with a list of numbers, right? And we can look at an example that shows exactly this, right? So if we just imagine their list of numbers as a separate type, list number and list integer, right? And then when we have add method, the type parameter becomes number here, and the return type of get is number here. And instantiate with an integer, add method takes an integer, get method returns an integer, right? And we see the problem with subtyping, right? Because it's not a true subtype, right? So true subtype would have had super type parameters and subtype return. So there's no problem with the return type. Integer and list of integers is indeed a subtype of number from list of numbers. Right? That's why they're shown in blue here. But here, for the parameters, we have a problem. Right? So if list integer is a subtype, it should have super type parameters, but it does not. Integer is not a super type of number. It's the opposite. Integer is a subtype of number. And that's why they are in red. These things break our subtyping guarantee, and that is, that demonstrates that no list of integers is not a subtype of list of numbers. Right? And here's a specific example that shows why it might look like an artificial restriction, but it's actually not, because we can see that if we allow this to happen, we would have a problem. So here's an example. We have an array list of dogs, okay? So far so good. And we have a list of animals, right? If we allow the list of dog to be treated as a subtype of list of animals, then this assignment would be legal, right? That would be just, subtype polymorphism, all right? If list of animal is a supertype of list of dogs, this is a valid assignment. So now, see what happens. Using animals, we can add a cat to this list, right? Because as far as their static type of animals, it's a list of any animals. Cat is an animal. We can add cat to animals list. And of course, now hopefully see the problem. Well, what happens when we take out this element from dogs? But dogs and animals is the same list. So we were able to put a cat in a list of dogs by using an alias, by using animals. And now when we get the element from our list of dogs, it turns out it's a cat, right? And we are assigning a cat to the dog. And yeah, that's not good. That should not be ever allowed, right? It's not surely type C. Right? That's why in Java we sort of need a special syntax to indicate when we actually want this inheritance to happen, right? By relaxing the standard rules, which would say like list of dogs is not a subtype of a list of animals. So this question mark, it is only used at the instantiation side, not at the declaration side, right? So when we are instantiating a type, we can specify, well, question mark extends E, for example, right? Or question mark super E. It can go, unlike bounded types, it can go both ways. It can use extends or it can use super. So basically, what we represent with this question mark is an anonymous type variable. So we're saying this is some variable, all right? That would be some type that extends E or that is a super class of C. And the idea is to let us, this wildcard allows us to actually solve this problem that we saw earlier with the copy method. Okay, that we wanted to be flexible, which bounded types were not letting us, but we at the same time wanted to ensure type safety. So here is an example when we want this add all method to be implemented such that it can take any collection, right? We want to instantiate this collection interface with the type argument. And we are using the question mark extends E because we are saying, well, we can take the collection of E or any other type that extends E. So what does this tell us about C, this collection that has elements that extend E? Well, that this collection may only have E or subtypes of E in this collection. Right, so we can also go in the opposite direction by saying question mark super, right? There are rules that say when we need to use extends and when we need to use super, right? So they are not interchangeable, right? So question mark extends E means some type that either is E itself or a subtype of E. Super means some type that is either E or a super type of E. Now with the introduction of wildcards, right, we can sort of translate it back to our covariance and contravariance that we covered earlier, right? So question mark extends introduces covariance. Question mark super would introduce contravariance, right? So in this example, right, we have apples as a declared type, a list of apples, and then we have fruits, which says, well, it's a list of anything that extends fruits. So apple is a subtype of fruit, apple is a fruit, strawberry is a fruit. So list of apple is a subtype of list question mark extends fruit. So you see, we took the responsibility by using the wildcard to say that, yes, in this case, a list of apples is a subtype of not just a list of fruits, but a list of all the types that extend fruits. And with that, we are now able to make this assignment, and this assignment is valid because this notation here says that fruits can hold the reference to any list that has fruits or subtypes of fruits as values. So if we have apples, yes, apple extends fruit, so fruits assigned apples is valid assignment. If we had a list of fruits themselves, that would also be a valid assignment. All right, now what the problem is, of course, is that this wouldn't compile, and rightfully so, because strawberry is not a fruit, right? So it's not going to compile. What about adding a fruit? Unfortunately, that won't compile either, and that is, strawberry is a fruit, right? But it's not going to compile. What if we try the fruit itself? Unfortunately, that wouldn't compile either. And that is a little counterintuitive, so let's make sure that we spend enough time discussing this, right? We are, I was hoping that we would go over the entire topic, but no, let's save it until let's finish next time on Thursday. In the meantime, you should be, with the information that we did cover, should be able to go ahead and